we know that the boiling point of a substance depends upon the pressure at which it is being kept. Usually we use complicated charts and steam tables, which have the value of boiling point or saturation temperature, for a wide range of pressures. These are determined empirically, that is through experiments. But a French engineer, Émile Clapeyron, was able to create a theoretical equation, which could show the mathematical relationship between temperature and pressure, for the process of phase change. This equation is called the Clapeyron equation, where delta H is the change in enthalpy during phase change, also known as latent heat, V is the volume, P is pressure, and T is temperature. Using this, if we know the temperature and pressure of any one point where phase change happens, we can calculate the saturation temperature and pressure at every other point where the phase changes. A German scientist, Rudolf Clausius, built upon the work of Clapeyron and applied the idea of the Clapeyron equation, specifically for phase change from liquid to vapor. This is called the Clausius-Clapeyron equation, where P is the pressure, T is the temperature, R is the gas constant, and delta H vaporization is the latent heat of vaporization. We can use this equation when liquid changes to gas, in order to understand the change in boiling point, for a given change in pressure, as long as the latent heat of vaporization is known. An important point to note, is that the log used here, is log to the base e, or the natural log. But in engineering calculators, this may be denoted as ln, while the button labeled log will actually give log to the base 10. We can derive the Clausius-Clapeyron equation from the first law of thermodynamics, and the equation for Gibbs free energy. We can write the first law in integral form, as du is equal to dq minus dw. From the definition of entropy, we know that delta S is Q by T, so Q is equal to T delta S. In integral form, this becomes dq is equal to T ds. The work done is defined as pdV. Substituting these, we get the following equation. Now, the Gibbs free energy is defined as H minus Ts. In integral form, this becomes dg is equal to dH, minus Tds minus sdt. Since enthalpy is U plus PV, we can write this in integral form, as dH is equal to du, plus pdV plus vdP. We can use the value of du, that we derived from the first law, which simplifies the equation as dH is equal to Tds plus vdP. Substituting this in the equation for Gibbs free energy, the Tds terms cancel out, giving us vdP minus sdt. Now, consider two phases, A and B. During phase change, both phases are in equilibrium. We know that when a system is in equilibrium, the change in Gibbs free energy for that process is zero. Or in other words, the Gibbs free energy is the same for both phases A and B. This is true in integral form also. We can use the expanded form of dg that we derived earlier. Let's bring all the dp terms to one side, and all the dt terms to the other side. Here, Sb minus Sa becomes the change in entropy, delta S. But since delta G is zero for the process, we can also say that delta H minus T delta S minus S delta T is equal to zero. Since the temperature remains constant during a phase change process, delta T is zero, and so the last term can be removed. Rearranging, we get delta S is equal to delta H by T. We can substitute this in the earlier equation, and rearrange, to get the following equation. If we think about the properties on a unit mass basis, that is, if we use specific enthalpy and specific volume, we get the equation known as Clapeyron equation. We can use it to find the slope between pressure and temperature, for any phase change process. If we consider that phase A is liquid, and phase B is vapor, then the volume of vapor is much greater than the volume of liquid. So we can ignore the V liquid term in the denominator, and simply write it as V. We can now rearrange this equation, in order to integrate. Since from ideal gas law, PV is equal to nRT, or pressure into specific volume is equal to RT, we can substitute V as RT by P. Rearranging again, we can integrate this equation. Taking the constants out, we get delta H by R, into T raised to minus 1 by minus 1 from T1 to T2, is equal to log P from P1 to P2. That is, log P2 minus log P1, or log P2 by P1, is equal to minus delta H by R, into 1 by T2 minus 1 by T1. This equation is known as Clausius-Clapeyron equation. It is used only for phase changes to and from the vapor phase.